thank you for inviting me to this workshop. I actually took part in this workshop a number of years ago in person. So this will be quite a different experience. Yeah, and it's going to be hard to go right after Danny, but I'm going to try. So this, as mentioned, this is going to be a 5 to 10 minute quick presentation followed by a discussion. So basically, what I'm going to talk about is the use of brain imaging data to predict phenotypes in individual participants. There's, of course, a growing interest in this topic. And in fact, today's session is all about that. One problem we have is that most prediction studies utilize small sample sizes. And there are two problems with small sample sizes. So first, small sample sizes lead to more variable results and worse reproducibility. And furthermore, if we're interested in predicting, making individual level prediction, it is well known that larger sample sizes lead to better prediction performance. So here's an experiment from the UK Biobank. My student He Tong trained different supervised learning models to predict fluid intelligence. And we consider different approaches, current regression and different deep learning models. Y-axis is the prediction performance. So higher the better, and x-axis is the number of training subjects. Oh, is that working? Oh, sorry. Okay, so as the number of training subjects increases, all regression models keeps improving. So if we want better prediction, we can just use a bigger data set. So the problem is that not everyone has a big data set, which motivates what we're trying to do. So our goal is then to somehow translate predictive models from big data sets to new unseen phenotypes in small data set. So this point about new unseen phenotype is quite important because why do people collect small data set? Because we want to study something different from the large data sets, right? So we do not want to simply translate a fluid intelligence prediction model from a large data set to predict fluid intelligence in a small data set. It will be much more useful if we can translate a fluid intelligence prediction model from a large data set to predict some other behavioral trait in a small data set. So He Tong's key idea is that the vast majority of phenotypes are not independent, but are intercorrelated. So here I'm showing the correlation among 67 non-brain imaging phenotypes in the UK Biobank. And indeed, many previous studies have found a small number of components linking brain imaging data and an entire range of phenotypes, such as cognition, mental health, demographics, and the health attributes. So in general, we expect that a unique phenotype from a small scale study would probably be correlated with some other phenotype in an existing large scale data sets. So to exploit these correlations, He Tong developed the meta-matching framework, where basically our goal is to predict a new phenotype in a small data set. So what we try to do is to first find the closest phenotype in the large data set. And we can then adapt the predictive models of this closest phenotype from the big data set to the small data set. And we find that this kind of a matching approach, meta-matching approach, gives very big improvement when we apply it to resting state function connectivity. So for example, this plot shows that a prediction performance using classical cone regression, right? So when you have 100 participants and 1,000 participants, we see that there's a big increase in prediction performance. And with meta matching, we can actually achieve the same prediction performance using just 100 participants. So basically with meta matching, we can boost the prediction power of a data set with 100 subjects to be similar to a data set with 1,000 subjects. So this was done with the UK Biobank. We have also shown that models from the UK Biobank can be translated to the Human Connectome project. So with a growing number of large-scale data sets collecting increasing diverse phenotypes, we are optimistic about the potential of meta-matching in boosting prediction performance in small data sets. Now, so far, we've shown that we can translate models trained from big data to small data, but it would also be useful to establish an upper bound on how well we can do if we have large quantity of data. Because if the prediction is already bad with large quantity of data, then meta matching is not going to help us. So what my other student Leon did was he used 1,800 participants from the ABCD study. He explored whether MRI modalities might be better for which MRI modalities might be better for phenotypic prediction than other modalities. So we computed, for example, anatomical volumes, anatomical thickness, and surface area from T1 images. We also considered various diffusion features such as fractional anisotropy, various Northeast features computed on TBSS skeletons, or probabilistic tractography. We also consider function connectivity computed based on resting and task fMRI. But in the interest of time, I'll just show you the performance from the best T1 features, the best diffusion features, and the best fMRI features. And we'll also show you the results from combining all fMRI data. So furthermore, we explore whether certain behavioral phenotypes are more easily predicted than other phenotypes. So here, Leon performed a factor analysis of 36 behavioral scores in the ABC study, and he extracted 3 factors corresponding to cognition, personality, and mental health. This factor analysis was done in a data set separate from this 1,800 participants. So y-axis is the prediction performance, larger the better. We see that here's the result for cognition, right? And we find that in general, function connectivity performs the best, followed by diffusion MRI and anatomical T1. And by combining all MRI, you perform even better. And this is also true for personality and mental health. Finally, it is a lot easier to predict cognition than other non-cognitive phenotypes. And we obtain similar results with the Human Connectome project. So to conclude, I've shown you that meta matching can effectively translate predictive models from big to small data. We have actually released a pre-trained model, which you can try out. We find that functional connectivity is generally better than anatomical T1 and diffusion features for predicting various behavioral traits. With relatively large sample sizes of 1,000, 2,000 subjects, cognition can be predicted quite well with an out-of-sample R of greater than 0.5. However, even with a relatively large sample size, non-cognitive measures cannot be predicted that well, with typical out-of-sample R of around 0.1 or 0.2. And actually, that's all I have. Thank you.
Thank you very much.